Okay everyone, I'm back to do part B and to put this puppy to bed. It's high time to finish it up and do the end game of the end game, so to speak. So here we are, and I thought that before I solve part B, I wanted to go back and actually talk about the problem and check my answer for part A. If you recall, this is the formula that supposedly will give the number of unique visitors to Facebook after T months after April of 2006. And we were asked to find the number of unique visitors when the number of unique visitors reached 1 billion. And we did some calculations and we came up with 43 months after April 2006, which just happened to be November 2009. And that means, since I'm talking right now in December of 2009, that if this exponential function does indeed capture the growth of Facebook's visitors, they have now gone beyond 1 billion unique visitors. So I thought we'd check the math. I thought we'd put 43 in here and see if we do get a billion out. And of course I'm being sly too, because the output here, if you recall, and it's true for a lot of these problems, has been massaged a bit. F of t, the output, is in millions. So when I put 43 in here, I'm not going to get out a billion. Rather, I'm going to get out the number of millions that are in a billion. And if you recall from part A, I had to actually figure that out to solve part A. And what I did was I dragged in a billion, and then I tossed a rectangle around this part because there are 6 zeros here, and this part represents the number of millions inside a billion. And so there's 1,000 millions inside a billion. And that should be the output when we let t equal 43. We ought to get 1,000 out here. I thought it would be interesting just to actually do it the way I did it in my head, using the skills of the course and getting one more last review. And so here is the tightest and slickest way to write a billion, 10 to the ninth. And here is a slickest way to write a million, 10 to the sixth. And this division essentially asks how many millions are there inside a billion. And of course, this is the second law of exponents. When you're dividing and the bases are the same, you subtract exponents. 10 to the 9 minus 6 is 10 to the 3, which is 1 followed by 3 zeros. And so once again, we get this nugget of truth. The answer we seek when we let t equal 43 is about 1,000. So let's run those numbers, and we'll go to Wolfram Alpha for that. And as you can see, here's the input, 43, and I'm asking Wolfram Alpha to give it to me to 4 digits, and here's the output. It's not quite 1,000, but recall that the t was rounded up to 43, and so there's an error introduced here, and you see that here. But the results are good enough to definitely affirm that our work was good in part A. So let's get on to part B now, and let me create some space. Here is part B. And for many of you, this is the more troublesome part of this problem. Essentially, what they're asking here is, what is the doubling time for the number of visitors? And this is a huge and valuable statistic for exponential equations. It's a real nice snapshot of what's going on up here. And we'll talk about more about that when we get there. For now, let's get it. And the way we're going to do that is find the initial number of visitors. In other words, what we're going to do is we're going to let t equal 0. That's where the clock got started. The initial condition was at t equal to 0. And so essentially we're going to let t equal to 0 in that function, and we're going to crunch it out. And this is what we get right here. When t is equal to 0, f of 0 is equal to 11.8. 11.8 million visitors, in essence, in April of 2006. And now what we want to do is double that, and then figure out the amount of time it takes to get to that new doubled figure. So really, what we want to do is double the initial condition. In other words, all I want to do is multiply that 11.755 by 2. Now, I'm not going to actually do the multiplication, and in a sense it's algebraically insane to do that, and you'll see why as I move down the page here. But I do notice that the textbook in the solution manuals actually will do this multiplication. If you need to see it, if you need to see 11.7 doubled, then go ahead and multiply it out. But watch how sweet the math works out if I don't do the multiplication. So now, to be sure of what we're after here, At time 0, there was 11.8, essentially, million visitors to Facebook. We want to know the new time that generates this doubled value. And so essentially what we're solving here is for t, and the equation is going to look like this. I want my output to represent the doubled initial condition, and I want to solve this now for t to find out how long it takes to get there. Now, the reason why I didn't do the multiplication, you can see that now. I can divide both sides by this. So, I'm all the way down to a very sweetly simplified equation. It looks like this. And I haven't had to touch a calculator yet. I reduced the chances of my errors by not actually doing this multiplication right here. And now, of course, here we are again, having to solve for a variable that's locked up as an exponent. And there's only one way to do that. It's a two-step process. The first step is you take the logs of both sides. And in this case, I'm taking the natural logarithms of both sides. And now this third law of the third law of logarithms says that you can rewrite, when you're taking a logarithm of a number that's to a power, you can rewrite that power out front as a product. And that's what I do. It's no longer trapped up as an exponent, and it's now solvable for, you simply divide both sides by the log of 1.109, the natural log of 1.109. And this is what you get. Whoops. This is what you get. And now we are definitely into calculator territory. And let me go to Wolfram Alpha for that. We crunch that out, and I've done it in advance. Here it is. I've asked for it to 2 places. And here's the result, 6.7. So, the answer to the question, the doubling time, is t is equal to 6.7. And that is in terms of months. So in 6.7 months, and every 6.7 months, the number of visitors, the number of unique visitors to Facebook is doubling. So think about this. If you're working for this business, that means in 6.7 months, according to this formula, which one of your departments figured out, you're going to have to increase your hardware to handle double the visitors. And then in 6.7 months, you're going to have to do that again. You're going to have to continue to scale your hardware to meet the new demand. So that's why doubling time is such an interesting statistic to pull out of an exponentiation function. And also on the other side, when they're shrinking, we're interested in their halving time, or if you will, their half-life. And there are some problems in the textbook that deal with that, but it's the same game. So I hope this helps. I'm just going to conclude with one more look at Wolfram Alpha. I wanted to sort of check this answer. And so I want to show you how I got at that check. Let's bring that in here. I think you'll find this interesting. Here is what I typed in. And I asked to go to 2 places. Now, when you do that, Wolfram Alpha rewrites it in a much cleaner format right here. And so you can see better what I was doing. On the bottom of the fraction, I have the number of visitors at time t equal to 0. On the top of the fraction, I have the number of visitors 6.7 months later. Now, theoretically, the top is going to be twice as big as the bottom. And when I do this division, the result ought to be 2. And as you can see, it is. And so, feeling very good about the answer here. Okay, I hope that helps. And thanks for being a student. And good luck in your future math courses.